Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 25 of quantum mechanics, in which I'm going to discuss scattering. Okay, and also I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, so I'm going to start now. Okay, this is scattering, right? Scattering. Okay, so I'll draw a diagram for it as well. Okay, so I'm going to draw the diagram. This is the target. Okay, these are electromagnetic waves or radiation. Okay, and this goes like this. Stream of particle we can say. Okay, and these are going to scattered with the target element. Okay, this one like this. Okay, and these are the waves, and the intensity of the wave or the stream of particle, okay, is I naught, and these are the scattered wave or scattered particles. Okay, and this. Okay, so this is outgoing flux, outgoing flux, outgoing flux. Okay, and this is incident flux, incident flux. Okay, so it's outgoing flux, it's incident flux. Okay, incident flux means the number of particles per unit area per unit time. Okay, and outgoing flux means number of particles scattered. These are number of particle incident per unit area per unit time, and this is number of particles scattered per unit time per unit area. Okay, so these are outgoing flux and incident flux. I'll write here number of particles, number of particles scattered per unit area per unit time. Okay, so this is the flux, number of particles, outgoing flux it is called. The number of particles scattered per unit area per unit time. Okay, and incident flux means here number of particles incident per unit area per unit time. Okay, this is per unit time. Okay, so this is the scattering, right? So the incident beam of particle strikes on, collides with this target, right? And the particles get scattered, right, in different direction with different energies. Okay, so this is the outgoing flux, this is the incident flux, number of particles incident per unit area per unit time. Okay, well, meanwhile, just let me check I'm audible or not. Particle, okay, is I naught. Yes, I'm audible. And these are the scattered wave or scatter. Okay, so I'm proceeding further now as I'm audible. Okay, well, next point. So I'll write a monochromatic or a mono energetic beam. A monoenergetic beam is incident. Beam is incident. A monoenergetic beam is incident on a target, on a target, on a target. Then particles of beam, particles of beam, particles of beam are scattered, are scattered, are scattered at different angles, at different different angles with different energies. Okay, with different energies. Okay, this is this is shown in the figure. I have shown in the figure. Okay, so this is the monochromatic energetic beam is incident on target. Okay, and then particles of beam are scattered at different angles with different energies. Okay, so these particles are scattered at different angles with different energies. Okay, this is the scattering, guys. Okay, so here we know these angles, right? This is, if this is r, this is theta, and this is going to be r d theta, right? This we know, r d theta. So there is a solid angle as well in similar way. Okay, so this is the case, this is the surface. Okay, and this is the angle d omega, and this is r. Okay, so in that case, d omega is going to be sine theta, d theta, and d phi. This is solid angle. Okay, this is d omega, guys. D omega, solid angle. Okay, so now differential cross section, very important. Okay, differential cross section. So differential cross section, differential cross section. Okay, differential cross section is d omega sorry, d sigma, my apology, this is d sigma upon d omega, okay, that is called differential cross section, and this is equal to outgoing flux upon incoming flux, incident flux, okay, incident flux, outgoing flux upon incident flux, okay. So this is the differential cross section, or we can write d sigma upon d omega, d sigma upon d omega, this is going to be I upon I naught, okay. So this is incident flux, sorry, it's scattered flux, right, that is outgoing flux, upon incident flux, okay. So I upon I naught, right. So from here we can get sigma, value of sigma, that is integration I upon I naught d omega, okay, and its unit is barn, okay, and one barn is equal to 10 to the power minus 2 meter square, okay. So this is the sigma, value of sigma. Well, now quantum mechanical representation, okay. So how a quantum mechanical representation, this is quantum mechanical representation, quantum mechanical representation of scattering, okay. So this, as we know, psi, that is the incident, the wave function of incident wave, right, this is e to the power I kz, or in 3D it is or e to the power I kr, okay, this one, and k we know, right, k is 2me upon h cut square, or that is momentum upon h cut, right, this also we know. So here incident beam treated like free particle or plane wave, okay, or plane. So incident beam is treated like free particle or plane wave, okay. So quantum mechanical representation we are studying, okay. Next is, so here I'll show you this one, okay. So this is target, okay, this is plane wave, okay. So beam of particle, you can consider it as a plane wave, okay, plane wave, okay, and this is also plane wave, which is unscattered plane wave, okay. And this is here scattered wave is going to be also plane wave, or this may be spherical wave, okay? Spherical wave. So plane wave or spherical wave, yeah? Spherical wave. spherical wave. Okay, so here we can write psi in, that is instant wave function, that is e to the power I k r. Okay, and psi scattered, psi sc, that is incident wave, that scattered wave function, that is that value is function f, which is function of theta and phi, e to the power I k r upon r. Okay, so total wave function is going to be psi, that is going to be psi in, that incident wave psi in plus psi sc, that scattered wave. Okay, and so we'll put the value. So this is going to be e to the power, psi is going to be e to the power I k r, will take common, so this is going to be 1 plus f, which is function of theta and phi, okay, upon r. Okay, so this is the total wave function. Now probability current density. Okay, probability current density, probability current density of incident wave we are talking about. Okay, probability current density, that is J equal to h cut k upon m z cap. Okay, so incident flux is going to be, then incident flux that is number of particle incident per unit area per unit time, right? That is I naught is going to be incident flux, I naught is going to be integration J naught, okay, you can J naught dot ds. Okay, so we put the value, so this is going to be h cut k upon m, and this is going to be, this is the value of J naught, right? This is, and z cap into ds, right? ds, z cap into ds. Okay, so this this value is going to be, this is going to be integration h cut k upon m integration ds. Okay, so this is the value of I naught, okay, this is the value of I naught. Next, incident flux. Okay, and so now probability current density, corresponding to scattered wave function. Okay, corresponding to scattered wave function. Okay, so scattered particles. So current probability current density corresponding to scattered wave function. Okay, so that is, so this is going to be J This is J naught, guys. Okay, J naught and incident, and this is J. J is going to be h cut k upon m, function of theta and phi, mod square of function of theta and phi, that is f theta and phi, okay, upon r square r cap. Okay, this is the one. Or we can write this is probability current density. Okay, or then this means I, and then I value of I is going to be h cut upon k upon m integration. Okay, so I is going to be integration like this, right? Integration j dot ds, right? So integration f theta phi mod square of f theta phi upon r square. Okay, and this is going to be, and this is function d omega, that is r square sin theta d theta d phi and dr, right? This is the one. This is I, outgoing flux. Okay, so I is going to be h cut k upon m integration f, which is function of theta phi mod square d omega. Okay, this one. Okay, so this is the value of outgoing flux. Okay, so now the value of d sigma differential cross section, okay, so d sigma upon d omega, right? So that is that is we know, right? That is this value is this. Okay, that we know, that is I naught, my apology, this is I upon I naught, right? Outgoing flux upon incident flux, that I have already explained. So we'll put the value, and this is going to be h cut k upon m integration f, which is function of theta and phi d omega upon h cut k upon m. Okay, so from here d sigma value of value of d sigma upon d omega is going to be integration f, which is function of theta and phi mod square d omega. Okay, so from here we can get the value of sigma, and that value that is going to be integration f mod square of f, which is function of theta and phi function. Okay, and that is d omega. Okay, so this is the very important, you need to note down. So this is the value of sigma. Okay, this is the value of sigma, and definition of sigma is also very important. So this is total number of particles. Sigma is total number of particles scattered. Very important. I will solve question. A question is asked in NEET 2015, which I'm going to solve, okay, today. So this is total number of particles scattered upon time into incident flux. Okay, incident flux, very important, guys. Sigma equal to total number of particles scattered upon time into incident flux, or in definition we can write like this: sigma equal to total number of particles, total number of particles, total number of particles scattered per unit time, per unit time, per unit time, per unit, and per unit time, and per unit incident flux. Okay, incident flux. So total number of particles scattered per unit time and per unit incident flux. Okay, so this is the definition of sigma. Okay, and this is the value of sigma also. Okay, integration function of the mod square of f, which is function of theta and phi d omega. Okay, well, now we are going to study attractive square well potential. Okay, attractive square well, attractive square well potential, attractive square well potential. Okay, so we'll define this potential. Okay, so this is VR is defined as minus V naught. Okay, if R is less than or equal to A, or this VR value is 0 if R is greater than A. I will make a diagram as well. Okay, so that it can clear your doubt. Okay, so this is like this. Okay, this depth is V naught minus V naught. Okay, and this is first region, and this is second region, right? And this value is this one. This value is 0 to A. Okay, in this region the potential is minus V naught. Okay, out of this region it's 0. Okay, this is second region and this is the first region, and there is an energy. Okay, like this is energy which is greater than V naught. Okay, greater than V naught. So this is how the attractive square well potential is defined. Okay, now we will get the Schrodinger equation for this, right? And then we'll get the solution as we did in infinite potential square well and other different types of potentials. Okay, you can check my previous lectures, you will see. Okay, now so the Schrodinger equation, Schrodinger time dependent equation is going to be for this. Okay, that is going to be 1 upon r square. Okay, in spherical coordinate. Okay, 1 upon r square upon 1 upon del r into r square del upon del r psi. Okay, plus 2m upon h cut square E minus VR psi equal to 0. Okay, so this is the Schrodinger time independent equation. Okay, now here we'll make some replacement. Okay, so suppose let psi r, which is a function, psi is a wave function, which is a function of r. Okay, wave function psi r equal to ur upon r. Okay, this we suppose. Okay, so let's consider this value is this. Okay, for solving this equation. So in that case, such that u naught, u at r equal to 0 value is 0. Okay, since we know, right, this Schrodinger equation, that is del square psi plus 2m upon h cut square E minus VR psi equal to 0. That we know, right? So in del square, because it's in spherical form, right? So we have put this value, okay? Right. So we've got this. Now we have now the value of psi r is UR upon R, okay? That potential U is function of R, okay? Now we'll put the value. So this is going to be, okay, this is going to be 1 upon R square del upon del R, okay? And this is R square, say this equation is 1, okay? R square del R upon, my apology, this is del upon del R, okay? Del upon del R, del upon del R, or instead of psi, we'll put this UR, U which is function of R upon R, plus 2m here, because if you put this value, now there would be one more term which we will subtract, that is minus L square upon H cut square R square, okay? Or we can just write this as well, it's okay. So okay, so this value is going to be this, okay? There's a term, okay? And then this is going to be plus, this is UR, okay guys, this is UR. Right here, minus this, and then UR by R, U which is function of R upon R, and plus 2m upon H cut E minus V psi which is function of R, okay, equal to 0. Now for S wave only, okay, for S wave scattering, we are just considering only S wave scattering, okay? Scattering, this value is going to be 0, okay? L is going to be 0. S wave, L equal to small l equal to 0. So this L is going to be 0, okay? So then the equation is going to be 1 upon R del square U upon del R square. U is the function of R, okay guys? So plus 2m upon H cut square E minus V which is function of R equal to, here we have done some mistake, let's just wait. This one, this value is 0 UR, okay? So this value, before that, first this one is correct. So now here this value is going to be, so since 1 upon R square del upon del R square del upon del R, this value del upon del R UR, U which is function of R, okay? UR upon R, this value is going to be equal to 1 upon R del square U upon del R. U is the function of R, guys, okay? This value. Now we'll just put this value in this equation, okay? And this value is going to be 0 because L is 0 here, okay? Because it is for we are solving it for S wave scattering only, okay? So this is going to be, then this is going to be 1 upon R square del square U upon, this is del square U upon del R square plus 2m upon H cut square E minus VR, okay? And this is U upon r equal to 0. Use the function of r. Okay, I'm just writing u r upon r like this. Now I'm just writing u here. Okay, so I'll write u, this will be better, u which is function of r, u which is function of r. Okay, so this is the equation. Now this is 1 upon r, guys. Okay, now we'll solve this equation. So this is going to be del square u, which is function of r, upon del r square plus 2m upon h cut square e minus v, which is function of r, into ur. This is going to be equal to 0. Okay, well, so this is the equation. Now what we are going to do, now we'll discuss region 1, region 2 one by one. Okay, first we are discussing this region 1. Okay, this one. Okay, so for region 1, for region 1 we have Vr equal to V naught, right? Here the Vr value for this region, the value of potential is minus V naught. Okay, Vr equal to V naught. Now we'll put this this value in the equation. You can say this equation is 2. Okay, so we'll put the value. So this equation is going to be del square, this is first region, right? So I'm just writing u first. Okay, u is function of r, u first upon dr square plus 2m upon h cut square and e plus v naught, u first, u1 or u first r. Okay, this is function of r, so this is going to be 0. So from here the value of u first, okay, that is, this is going to be, which we know, right? If we, so this value will take k, right? And then we'll solve it, and then value of d is going to be plus minus iota k, right? And directly I'm going to write solution. So this is going to be, u first is going to be a sine k1 r plus b cos k1 r. And where the value of k1 is we have put k1. Okay, so k1 is root 2m e plus v naught upon h cut square. Okay, so this is the value of k1. Simple, we have already done in many times, right? In my previous lecture you can check it. So this is the value of k1, guys. Okay, next, this is the value of k1. Next is, so here we can write this as well, k1 square. K1 square we can write, so we can square it, right? So this is going to be 2me upon h cut square plus 2me mv naught upon h cut square. Okay, so we have just opened this, that we have square in both sides. Okay, so and so k1 square is going to be, so that this is k naught square. Okay, let's suppose this is the value of k naught square, my apology, this is k square. Okay, k square and plus this is k naught square. Okay, let's say, so this value, this is k square and this is k naught square. Okay, now we'll use this using partial wave method, using partial wave method in the second region, second region. Okay, the value of this u2. Okay, this is the u2. Okay, this is going to be u is function of r. Okay, this is going to be c sine, I'm writing it directly guys, very lengthy. Okay, kr plus delta naught. Okay, so this is the second wave. Okay, well here we have to do some correction here. This wave, so here this is the value. Right now here we can write one more step, that is at r equal to 0. Okay, u first is going to be 0, right? This is 0. So from here we can see the value of b is going to be 0. It means u first value is going to be a sine k1r. Okay, k1r. How? Because here if you put r equal to 0 here, okay, at r equal to 0, this value is going to be 0, right? So if you put here sine 0 value is 0, right? Then it means a is not 0. Here cos this is cos kr, right? Cos 0 is 1, right? It means because this complete value is 0, right? It means this is 0 because of sine, right? This means b must be 0, right? So that's why at r equal to 0, u first equal to 0, that implies b equal to 0, because this is value 1, right? R equal to 0. So it means for getting this value 0, b must be 0. It means this wave function u first is going to be a sine k1r because b is 0. Okay, well, so this is the u second. Now we'll use boundary conditions. Okay, at r equal to a u1. Okay, u1 is going to be u1 is going to be equal to u2, right? And similarly del u upon del r at r equal to a, these boundary conditions I have already explained. Okay, so this value is going to be del u, this is first, okay, del u second upon del r at r equal to a. These are the boundary conditions. Okay, so simple. So now first we'll find this u1 and u2, right? So this is going to be this is u1 guys. Okay, and this is u2. So this is going to be a sine k1a. This is a sine k1a at r equal to a, right? A sine k1a, first boundary condition we are using, this first one, u1 equal to u at r equal to a. Okay, a sine k1a is going to be equal to this is kc cos ka plus delta. This is kr plus delta kr plus delta naught. Okay, kr plus delta naught. We'll find the value of delta naught, guys. Okay, so this is delta naught. Okay, well, so this is this you can say equation number 3. Okay, this is I think we've made some mistakes. So this is the value, this one, c sine kr plus delta. Okay, so u2 we are writing, we have not differentiated at the time. So c sine this one kr plus delta, c sine kr plus delta naught. This is equation number, I think, how many equations we have? 2, right? So third, equation number third. This is equation number third. Okay, now second condition will use this one, will differentiate these two this one at r equal to a and this one at r equal to a, right? So after differentiating, this value is going to be k1a cos k1a. Okay, we have differentiated, and this is going to be kc cos kr plus delta naught, and this is equation number 4. Okay, now we'll do equation number 3 by 4. Okay, 3 by 4. So this is going to be 10 k1a upon k1 is equal to 10 kr plus delta naught upon k. Okay, because sine upon cos equal to 10, right? So this is the one. So now we can further solve it. Okay, so this is going to be, this value is going to be 10 ka 10 ka plus 10 delta naught. Okay, we are just we have opened this formula. Okay, 10a plus b. Okay, we have taken this in right hand side and then opened it. 10 delta naught upon 1 minus 10 ka into 10 delta naught. Okay, 10 delta naught. Well, so this is going to be equal to this one, k upon k1, k upon k1. Just a simple calculation, guys. Okay, so just I have just opened it, right, and cross multiplied, right? So k upon k1, and then that is 10 k1a. Okay, and since we know that I have already explained k1 square equal to k naught square, k square plus k naught square, k naught square, right? So at low energy, okay, at low energy and S scattering, right? This value of k1 is going to be, k1 square is going to be almost equal to k naught square. Okay, and 10 delta naught is going to be almost equal to delta naught, and 10 at low energy we are talking about. Okay, so 10 ka is going to be ka. Okay, so now we'll put these values here. So this is going to be ka plus delta naught, this is k delta naught, right, upon 1 minus ka delta naught, and this is going to be k upon k naught, 10 k naught a. Okay, well, next value is going to be this one, ka plus delta naught equal to 1 minus ka delta naught k upon k naught, 10 k naught a. Okay, we'll just multiply that. So this is going to be ka plus delta naught, k plus delta naught is going to be equal to k upon, will multiply it, right, k upon k naught, k upon k naught, 10 k naught a minus ka delta naught k upon k naught, and that is going to be k square. Okay, so k square, I'll directly multiply and write it. This is going to be minus k square a delta naught upon k naught into 10 K naught A, and this value is very small, guys. Okay, very small, so we can neglect it. Okay, very small. So from here, the value is going to be Ka plus delta naught is going to be K upon K naught. This is ignored, right? So this is K 10 K naught A. Okay, and from here the value of delta is going to be value of delta naught is going to be Ka into 10 K naught A, Ka into 10 K naught A upon K naught A minus 1. Okay, very important formula. Minus 1, this one. This one. Okay, so now this is delta naught equal to Ka 10 K naught A upon K naught A minus 1. Very important. Now there's a formula for sigma, right, which I have already explained, right? This value is 4 pi upon K square. Okay, sigma L equal to 0 to infinity 2L plus 1. Okay, and sine square delta naught. Very important formula, you need to note down this as well. Okay, so here this delta naught value we can put from here. Okay, so this is sigma equal to 4 pi upon K square, sigma L equal to 0 to infinity 2L plus 1 into sine square delta naught. Okay, this is very important. Now so we'll discuss for S wave scattering, okay, or low energy and low energy. So for S wave scattering, value of L is going to be 0. Okay, so this value is going to be 0, then sigma, the value of sigma is going to be 4 pi upon K square sine square delta naught, because L is 0. Okay, so this is the value, and now we'll put the value and here we'll put the value of delta. Okay, so sigma value is going to be 4 pi K square, and here also this one, because for S wave scattering, sine square delta is going to be almost equal to delta square. Okay, so here we can write 4 pi delta naught square. Okay, delta naught square. So we'll put the value of delta naught. So it's 4 pi upon K square into value of delta square is K square A square. Okay, into 10 K naught A upon K naught A minus 1 whole square, right? This one, because value of delta is this, right? So whole square means K square A square and 10 K naught A upon K naught A minus 1 whole square, right? This one, K square will get cancelled, and then value of sigma for S scattering is going to be 4 pi A square 10 K naught A upon K naught A minus 1 whole square. Okay, so this is the value of sigma for S wave scattering. Very important formula to solve questions. Okay, this one you can note down. And similarly, if there is a trick I'm telling you. Okay, trick is if for repulsive force. Okay, repulsive force, my apologies, for repulsive potential, for repulsive potential, right? So we have got the value of sigma for attractive potential, right? So this one, for this is the attractive potential we have discussed, right? This one, this is the attractive. So instead of attractive potential, if it is repulsive potential, then we will not do this lengthy calculation, right? The lengthy derivation. We'll use trick, right? And we can easily get that. So for repulsive, that trick I'm telling you. Okay. So for repulsive potential, okay, minus V naught is going to be equal to V naught, right? Because that repulsive means plus, right? For repulsive, that minus V naught is going to be V naught, right? So here the value of K naught will be, that is we know that 2m V naught upon h cut square, which I have already explained. That is the value of K naught, right? Now if you put that, because if it's an attractive potential, then this is going to be minus sign, okay? So this is going to be, then value of K naught is going to be, in case of that, in case of repulsive potential, so if you put this one, this is going to be 2m V naught upon h cut square and minus into, okay, this one, okay, if it's attractive potential. For attractive potential, V minus V naught is going to connect to V naught, okay. So this one, so there is minus in root, means iota. So this value is going to K is going to be iota K naught in case of repulsive potential. So K naught is going to be iota K naught. So we'll put iota K naught here. We'll get this value of sigma. Okay. So value of sigma is going to be, just give me 1 second, guys. Please, Anisha. Okay, guys. Thank you. Well, so then what we'll do is, instead of K naught, we'll write iota K naught and we'll get the value of sigma for if it is a repulsive potential instead of attractive potential. Okay. So I'll write it. So sigma is going to be that is, that value I'm going to write directly 4 pi a square, and I'll explain how I have it. Okay. So that is 10 hyperbolic K naught a, okay, upon iota K naught a minus 1 whole square. Okay. Here what we have done is, if you put this is going to be 10 iota K naught a, right? And 10 iota K naught a, if you change it, that value is going to be we can change. I'll show you here. 10 iota K naught, if it is there, so we can write is 10 hyperbolic K naught. Similarly, if we have sine iota K naught, it means sine hyperbolic iota K naught. This we have also studied in complex analysis, right? There are some questions we have solved. Okay. So 10 this here 10 iota K naught, that value is going to be 10 hyperbolic K naught a. Okay. So this is 10 hyperbolic K naught a upon iota K naught a minus 1. This is the value of sigma in case of repulsive attractive potential. Okay. Next point. Next is okay. So potential for if there is a hard sphere, okay, hard sphere or impenetrable penetrable potential. Okay. Right. So this is for hard sphere. For hard sphere, or we can say which is impenetrable, which cannot be penetrated, right? That is called impenetrable. Okay, impenetrable potential. That is which is hard sphere. Okay, so potential. If there is a hard sphere or impenetrable potential, in that case, VR is going to be, which so we can define VR, right? That is going to be infinite, because we cannot penetrate it, right? Infinite if R is less equal to A, right? In the radius of a sphere, okay? Because it's very hard or impenetrable, okay? So that VR is going to be infinite. That's why we are not able to penetrate it, right? And or zero value is going to be zero if R is greater than A, right? So in that case, we'll find this one, right? So in that case, K naught is tending to infinite, okay? So and K naught value we know, right? K naught equal to 2me upon h cut square, and so it means the value of 10 K naught is going to be, I'm writing here, okay, 10 K naught A, this value is going to be that is 10 K naught A, or that e to the power K naught A minus e to the power minus K naught A. The value of 10 K naught A is this, right? We know 10x equal to e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x, right? So same thing, 10 K naught A with x instead of x, there is K naught A, okay? E to the power K naught A minus e to the power minus e to the power K naught A upon e to the power K naught A plus e to the power minus K naught A. This value is going to be almost equal to 1 when K naught tends to infinity, okay? So in that case, sigma is going to be, value of sigma is going to be, for hard sphere I'm talking about, okay? It is 4 pi a square, and this value is going to be 1 upon iota K naught A minus 1 whole square, because this value is this one, right? This value is going to be almost equal to 1. So this value is going to be, this is K naught is infinite, right? This value is 0, whole square is 1. So it means the value of sigma is going to be 4 pi a square. Okay, this is the sigma value. Well, and there is a trick also. I'll write this trick. So this is for and trick is sigma value is going to be 4 pi a square for low energy, okay? For low energy, okay? And sigma value is going to be 2 pi a square for high energy, okay? If energy is high, this is for if energy is low, guys, okay? If energy is high, then higher energy, this value is 2 pi a square. And for classical, the value of sigma is going to be pi a square for classical or geometrical, for classical case, okay? For classical case, classical oblique geometrical, classical oblique geometrical. This is the value of, these are the value of sigma in different cases, okay? Now I will solve question, then your doubts are going to be clear, okay? Question first is, okay. Question first is, consider an elastic consider an elastic scattering. Elastic scattering means there is where there is no loss of energy, okay? So consider an elastic scattering of particle in L equal to 0. L equal to 0 is given means this is S wave scattering. Okay, L equal to 0 means S wave scattering. Okay, in because I have already explained S wave scattering means L equal to 0. Okay, so scattering of particle in L equal to 0 state. Okay, if corresponding phase shift that is we are talking about phase shift is delta naught. Okay, phase shift, if corresponding phase shift is that is delta naught. Okay, delta naught is a phase shift, guys. So it is pi by 2. Okay, magnitude of incident wave vector is given. Okay, the magnitude of incident wave vector is root 2 pi. Okay, that is Fermi inverse. Then total cross section. Okay, total cross, that is sigma we are talking about. Okay, total cross section. So total cross section in unit of Fermi square is. Okay, so this is the question. Consider an elastic scattering. So we are considering elastic scattering of particle in L equal to 0. That is we are talking about S wave scattering. Okay, if corresponding phase shift is given, that is delta naught is given, the magnitude of incident wave vector is also given, and we have to find that is the cross section. Okay, then total cross section. Okay, so we have to find total cross section. Then total cross section. Okay, sigma we need to find out. So we have a formula, guys. Okay, so we have a formula that is sigma equal to 4 pi upon k square. You need to note down. Okay, sigma L equal to 0 2L plus 1 sine square delta naught. Okay, so this is the formula I have already explained, right? Here L equal to 0, right? So it means this value is going to be, value of sigma is going to be 4 pi k square into sine square delta naught, right? Because this value L is 0. Okay, so here 4 pi upon k square sine delta naught is given, right? Phase shift is given, so that is sine pi by 2 square or sine pi by 2 whole square, right? And this value is 1, so this is going to be 4 pi upon k square, and initial this is also given, the magnitude of incident wave vector, that is k is given. Since k is given, that is root 2 pi, right? So k square is going to be 2 pi, right? So here we will put the value. So sigma is going to be 2 pi upon 2 pi, that is 2. Pi will get cancelled, and so sigma value is 2, guys. Okay, options are. Now I'm going to solve question which is asked in NET 2015. Okay, CSIR NET 2015. Okay, so question is CSIR NET 2015. This is the question, and this is the question related to total scattering. Okay, the differential cross section, the differential cross section for scattering differential cross section for scattering by a target by a target is given by d sigma upon d omega, that is given, okay, which is function of theta and phi, okay, that is given a square plus b cos square theta, okay, a square plus b cos square theta, this is given if n is the if n is the flux, n is the flux of the incoming particle, it means n is the incident flux, okay, so n is the flux of incoming particles, okay, the total number of particles scattered per unit time is okay. So this is the question. Options are given. Options are 4 pi n. Option A is 4 pi n by 3 a square plus b square, okay. Option B is 4 pi by n 4 pi n upon just a 4 pi n, okay, 4 pi n into a square plus b square by 6. Option C is 4 pi n a square by 2 plus b square by 3, and option D is given, that is 4 pi n a square plus b square by 3, okay. So these are the options. The question is the differential cross section is given, okay, the differential cross section for scattering by a target is given by, okay, this d sigma upon d omega is given this, okay. If n is the flux of incoming particle, means n is incident flux, that is given. The total number of particles scattered per unit time we need to find out, okay. So here first I already explained, that is sigma value is that is total number of particle scattered total number of particles scattered upon time into incident flux. I have already explained earlier, okay. So this is sigma, okay. From here, this is total number of particles scattered upon time, or we can say the total number of particles scattered per unit time per unit incident flux, okay. From here we can get this, from here sigma into suppose the incident flux is I naught, okay, okay. So sigma into I naught is going to be total number of particles per unit time, right? Total number of particles scattered per unit time, right? So if we get this value, sigma value, right, and if you multiply this with n, that is I naught, right? I naught is the incident flux, and incident flux is given here, that is n, okay. This one n is given, right? So we can easily find out, right? So this value is this total cross section into incident flux, right? So now what we are going to do is what we have been given. We have been given d sigma upon d omega. We just have to find the value of sigma and we'll multiply, and then what we'll do is we'll multiply that value of sigma with incident flux. We'll get the required value, that is total number of particles scattered per unit time. Okay, so d sigma upon d omega is given, guys. It's a simple integration. Okay, so it's a square plus b square cos square theta. Okay, have we made any mistake? So this, no, this is b square, guys. Okay, b square. Okay, so simple now. So from here value of sigma is going to be integration a square plus b square cos square theta d omega, right? This we know because we'll take this side, right? Simple thing, we have integrated it. Now we'll integrate it, right? So this is going to be sigma equal to simple integration. Okay, so this is going to be a square, will take outside, you know, so, a square, and this is going to d omega, right? It's going to be 0 to pi, 0 to 2 pi, and 0 to okay, 0 to pi, 0 to 2 pi only, because theta, this is function of theta and phi, right? This is sine theta d theta, right, and d phi, plus double integration b square will take common. I'll tell you how I have done. Okay, this is 0 to pi, 0 to 2 pi, b square is common. Okay? This is cos square theta, this is sine theta, d theta, d phi, right? Because here this is function of theta and phi, right? So value of d omega is going to be sine theta d theta d phi. Okay, this is the value of d omega. Now simple integration, guys, right? So this integration we know, and in spherical coordinate system as well, right? If theta is, if phi is there, its limit is 0 to 2 pi, theta 0 to pi, right? Okay, I have also explained this spherical coordinate system in my mathematical physics class. You can check that as well. Okay, so it's a simple integration, you need to do it. Okay, so this is going to be value of sigma is going to be this one. This is 4 pi a square, this is 4 pi a square. Okay, sin theta is cos theta, and this is going to be pi, and this is 2 pi. Okay, we'll write it. So 4 pi a square, and plus this value is going to be b square, and cos square will open that, we know that, right? Cos 2 theta equal to 2 cos square theta minus 1. So from here cos square theta value is going to be 1 plus cos 2 theta by 2, right? So we'll put here and we'll solve it. Okay, very simple integration. We have already done it in class 11th and 12th, right? So this value is going to be, if you write that, so this value is going to be or 2 pi, or directly the value, or you can also note down, okay, memorize it as well. So integration of cos square, okay, between 0 to pi, cos square sin theta, between 0 to pi is going to be this one, because we have cos square and sin theta, right? We can say let cos theta equal to t, right? And then we can get the value t square, right? And directly this value is, you can also note down, this is 2 by 3. Okay, cos square theta sin theta d theta 0 to 2 pi, that value is 2 pi by 3. Okay, and 0 to 2 pi value is 2 pi. Okay, so this is going to be 4 pi a square plus 2 will get cancelled, b square pi upon 3, right? v square phi upon 3, right? So now from here, from this equation 1, you can say this is equation 1. So total number of particles scattered per unit time is going to be, so this value is going to be sigma into n, right? Total number of particles scattered per unit time, suppose I can say n dash, okay? So this is going to be sigma into n, this one, suppose I say this is n, n dash, okay? Sigma into I naught. I naught is n, incident flux, that is given n here. Total, if n is the flux of incoming particle, means flux, okay? So this is sigma into n, so this is going to be n into sigma value is this 4 pi a square plus b square phi upon 3. So this is going to be 4 pi, and 4 pi you can take common. There is 4 pi, guys. This is 2 pi, right? 2 pi. 2 pi. Okay. So 4 pi. Yes, we'll take 4 pi n common, and this value is going to be a square plus b square by 3, right? So let's see this. Let me check. Okay. So this is the answer. 2 will get cancelled, right? 4 pi. Is there any mistake you are doing? Some mistake is happening. Just check. Number of particles studied. This is going to be 4, guys, right? This is 4. 1. Here some mistake. So answer is going to be this, guys. This one. 4 pi n a square plus b square upon b square by 3. B square by 3. So this is the answer, guys. So you can calculate this integration. Okay. I have to do one more question because I have time is already over. So I'm going to solve one more question, which is also asked in CSIR net. Okay, so you can solve it, guys. So this is the answer. Answer is D, guys. Okay, this one. There is some mistake, I hope. I'll correct it. So this one. This is the correct answer. D. 4 pi n a square plus b square upon 3. There may be some mistake here in this integration, guys. Okay, so you can say, like, you can put cos theta equal to t, and then you can put the value and you can easily integrate it, guys. Okay, because my time is already over, so I'm not doing that. I'm solving one more question. Okay, you can do it, guys. Very simple integration. Next question, question third. Question third is, this is also asked, this is asked in, this is asked in CSIR net, CSIR net December, CSIR net December 2017 question, guys. Okay, this one. This question is, a phase shift, a phase shift, a phase shift of 30 degree is observed. It's talking about delta naught. Okay, phase shift of 30 degrees observed when a beam of particles, of energy 0.1 mega electron volt is scattered by a target, by a target, by a target when the beam of energy, when the beam of energy, beam of energy uh, is changed, is changed. This is 5 marks question, guys, but very easy question. You can solve it in 1 minute. I'll tell you how. Okay, so but it's a 5 marks question which is asked in 2017. Okay, so when the beam of energy is changed, beam of energy is changed, the observed phase shift, the observed phase shift, observed phase shift is 60 degree. Okay, so when energy is 1 MeV, then the phase shift is 30 degree, and now we have changed that energy, right? And we've observed the phase shift is 60 degree. Okay, assuming that only S wave scattering, S wave scattering is relevant. Means we have to consider only S wave scattering. Means S wave scattering means L equal to 0. Okay, so only S wave scattering is relevant, and the cross section cross section the cross section does not change, cross section doesn't change with energy, the beam energies. Okay, the beam energies. Okay, options are option A 0.4 MeV, option B is 0.3 MeV, option C is 0.2 MeV, and option D is 0.15 MeV. Okay, I'll read the question again for you. So this is a phase shift of 30 degrees observed when a beam of particle of energy 0.1 mega electron volt is scattered. Okay, when this megavolt electron, when this energy uh, when a beam of particle of this energy is scattered, then we have got 30-degree phase shift. Okay, and when the beam of energy is changed, we have changed the beam of energy, and the observed phase shift is 60 degree. Okay, assume that only S wave scattering is relevant and the cross section doesn't change with the energy. Okay, and also it is given cross section doesn't change with the energy. Okay, this is very important point. Cross section is not changing with energy. Okay, the beam energies. Okay, this we need to find out. So here first I'll directly write for you. Here the energy is inversely proportional to 1 upon delta naught square. Okay, note down, this is important formula. Energy, that is energy E, is inversely proportional to 1 upon delta naught square. This is phase shift, this is energy. Okay, this is the relation of between the phase shift and the energy of beam of particle. Okay, this one. So from here we can easily write E1 upon E2 is going to be delta naught 2 square upon delta naught 1 square, right? Because this is the relation, okay? Delta naught 2 square upon this one. Now E1 upon, so we can write like this, E2 upon E1. E2 upon E1 is going to be delta 1 naught square upon delta 2 naught square, right? This is actually sine, guys, okay? Sine, my apology. This is sine. This is sine square delta naught, okay? So this is going to be, so from here we can find out this one. So this is, we can write directly E2 upon E1. This is going to be sine square delta naught 1 upon sine square delta naught 2, right? So E2 upon E1 is going to be sine square delta. So we have given value, right? This is 60 degrees given delta. So sine square 60 degree upon sine square. So this is, wait, this is sine square 60 degree. Have we done any mistake? Sine square 60 degree. Sine square 60, sine square 60. So here this we have made mistake, guys. This one. This is proportional to sine square delta naught. Okay, this is proportional to E proportional to sine square delta naught. So here this is going to be E2 upon E2 equal to 1. Okay, so this is going to be delta 2 and this is delta 1. So this is going to be sine square 60 upon sine square 30. Okay, so we'll put the value. So this is going to be sine 60 value is 3 by 2, right? And square is there, so this is going to be 3 by 4 upon sine 30 value is 1 by 2, so 1 by 4, right? So 4 will get cancelled, so E2 upon E1 is going to be 3, right? So from here value of E2 is going to be, value of E2 is going to be 3 into E1, okay? And E1 value we have already given, that is 0.1 mega electron volt, right? 0.1 mega electron volt. So we can write 3 into 0.1 mega electron volt. So this is going to be 0.3 mega electron volt E2. Okay. So which option is matching, guys? Option B. So here you need to so this formula you need to note down. The energy of the beam is directly proportional to phase shift. Okay. And so from here we can easily find that E2 upon E1 is going to be these values, right? And from here we've got the energy of second beam, okay, whose this one, okay, whose phase shift is 60 degree. So the energy is 0.3 mega electron volt. I hope you understood it, guys. Okay, well, okay, this is about anything missing or anything I can tell you. And this is okay, understand, guys, this is valid only if that this is not changing. Okay, this is not changing, the scattering is relevant and the cross section, okay, cross section doesn't change with energy. Okay, if cross section is changing with energy, right, in that case this formula is not valid. Okay, so E is proportional to sine square delta naught. Okay, anything I need to tell or remaining? No. Okay, so guys, I'm going to stop here. So scattering is completed, guys. You can solve questions, and I will also solve questions for you because I'm solving PYQs, right? So 2009 June 2019 and December 2019 PYQs are completed, so you can watch that. And so today onward, I'll start with the PYQs of June 2020. Okay. Okay, guys. So, well, so in next class we are going to study Born approximation. Okay, and after that relativistic quantum mechanics. And in 4 or 5 lectures, quantum mechanics is going to be completed. And the next class is going to be for mathematical physics. Okay, in which I'm going to discuss Laplace transform, Fourier transform, and Fourier series is completed. Okay, and that class is also going to be completed. That mathematical physics is also going to be completed almost in 5 or 6 lectures are remaining, right? And then mathematical physics will also be completed. And after that, I'm going to start condensed matter physics and thermodynamics and statistical mechanics. Okay. Well, okay, guys. So I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, guys, thank you so much. Bye now.